Okay, so we're going to talk about transforming and combining random variables, and really, like I said, it is a little bit nuanced, but the nuance is specifically in the difference between transforming variables and then combining two random variables. All right, so we'll start with some transformations first. You can think of a transformation as like when you're just converting units, okay? So um, if we talk about how tall you are, um, right? If I'm 6'4", I can convert my height to meters. I'm still the same height. I'm not changing anything about that data. All I'm doing is converting to a different unit in that case. That's a transformation, okay? And so here we're going to take an example for El Dorado Community College. And it considers a student to be full-time if he or she is taking between 12 and 18 units. And so the number of units X that a randomly selected community college student is taking in the fall semester has been or has the following distribution. So they could either be taking 12, 13, 14, 15, 16, 17, or 18 units. And we're given those corresponding probabilities. And if we added these probabilities up, they're going to add up to 1. So we know that this is a working probability model. All right, so we want to calculate and interpret the mean and standard deviation of X. I'm going to do this in my calculator. So we'll get mu of X, and we'll get sigma X. All right, and that'll give us some practice over kind of what we just went over. So let me pull up my calculator. I'll share that with you. You should practice along with me here. We're just going to enter our outcomes into list 1. We'll enter our corresponding probabilities into list 2. So I know that you can't see the screen anymore. Our outcomes were just the credits. That was 12 through 18. And then I'll tell you their corresponding probabilities were 0.25 for 12 credit hours, 0.10 for 13, 0.05 for 14, 0.30 for 15, 0.10 for 16, 0.05 for 17, and finally 0.15 for 18. All right. So now we have those in. We're going to go to the main screen, so I'll just quit. Remember, we want to do stat calc. We want one variable stats. And we want our list to be our outcomes list, which was list 1. And we want our frequency list to be our probabilities, which was list 2. Again, if you have the older operating system, it's going to look like this. Just pull up one variable stats and then do L1 comma L2. All right, and then we get our mean and our standard deviation. So 14.65 for our mean, 2.0, we'll round it to 2.06 for our standard deviation. All right, so our mean is 14.65 credits, and our standard deviation is 2.06 credits. So here's how I'm going to interpret the mean. After randomly selecting many students we would expect the average number of credits taken to be about 14.65 credits. All right, and you can word this in different ways, but the things you want to make sure you hit right are long run, and so I hit long run by saying we randomly selected many students, right? You want to make sure you're talking about a mean or an average or an expected value, and then you just want to make sure you have context, so you're not just stating a number, you're stating, in this case, that it's credits that we're talking about. And then for the standard deviation, I'll say a randomly selected student will typically deviate from the mean number of credits by about 2.06 credits. Great. So that's it. Remember, standard deviation is just typical deviation from the mean. All right. So tuition for a full-time student is $50 per unit. So we're going to let capital T be tuition. And tuition is a transformation of credit hours. So we have that T equals 50x. And so you can see what the corresponding tuition fees would be. The probabilities remain the same, right? So this is like tuition for 12 credit hours, 13 credit hours, 14, and so on up to 18. Oh, come on, computer, catch up here. Sorry. Okay. Give me a second. I'm going to try and switch over to a better. Sorry if I froze for a second. My computer switched to my Wi-Fi extender, which is in the other room with my wife, and that makes it, oh, it says it's still unstable. Okay, let's see if this works. Apologies. All right. So what we want to do is calculate the mean and standard deviation of this new random variable that's made by transforming the old random variable. So I'm going to do that in my calculator. Let's pull that up again. All right, let's go to stat edit. So here's what I want to show you. List 3, I'm going to highlight the name list 3, and that'll allow me to manipulate the entire list. And I'm going to say that list 3 is really the outcomes from list 1, which are our credit hours, times 50. Boom. You can see that just gives us our outcomes from our new table. So list 3 is now our tuition values for each corresponding credit hour, right? All right, and they say calculate the mean and standard deviation of t. So we can do this again. So I'm going to go to quit to the main screen. I'm going to pull up one variable stats again. But now my new outcomes are not in list 1. My new outcomes are in list 3. So I'm going to change my outcome list to be list 3. So you can use the shortcut on the keypad. But I want my probabilities are still the same, right? So that's still in list 2. So now I want to do one variable stats, list 3, comma, list 2. And so now we get a mean of $732.50. We get a standard deviation of $102.80, right? And so it's not asking me to reinterpret. We could reinterpret. The interpretation would be the exact same, except we would change out credits for dollars, and we would change out, so we would say the average tuition would now be $732.50 after randomly selecting many students, and a typical student would deviate from that by about $102.80. So the thing I want to point out is the relationship between the mean tuition and the mean number of credits. So if you just take this 14.65 and we just multiply it by 50, all right, so if we do 14.65 times 50, boom, notice that we get our mean tuition, right? And if we take the standard deviation number of credits, which was 2.06, and we also multiply that by 50, we end up with 103, which is only slightly different from our standard deviation here. And the only reason it's slightly different is because we rounded off that 2.06 credits, right? So that's just round off error. But the point there is that you can actually get the mean tuition and the standard deviation tuition without having to calculate it from the new raw data, right? We could have just converted our mean and standard deviation from the old mean and standard deviation. All right, and that's what we're stating here, which is multiplying or dividing, same thing. Each value of a random variable by a number b multiplies any measure of center and or location. So that means mean, median, quartiles, percentiles by b. Now, the one that we just showed was the mean, but it's really any measure of position it would have that same effect on. So it just multiplies it by that same factor of b. And it multiplies measures of spread by the absolute value of b. And that's just because your multiplier could technically be a negative value, but your measures of spread will always be positive. So you're always going to multiply by the absolute value of b. Now we know what we can do if the transformation is just a multiplier like this. We would just multiply the mean and standard deviation by that same value, and we would end up with our new transformed mean and standard deviation. Here's the thing about college. They love to charge you other things. So they will tell you what the fees are for tuition, which is per credit hour. But then you got all these other fees like your parking fee or whatever, campus. I can forget what they call it. It's just called like a campus fee, and that's so that you can use the gym or whatever. So at community college, those fees add up to $100 per semester. So we're going to define a new random variable, C. And C is the overall cost for a randomly selected full-time student, which would basically be their tuition plus the student fees, right? The $100. So C is just 100 plus T. And so here's the probability distribution for C. And all we did there, I'm going to pull up my calculator. Let's go back to our lists. Let's go to list 4. I'm going to highlight the name of list 4, and I'm going to say that list 4 is 100 plus list 3. So it's just our tuition plus you get the student fees of $100. And there we go. Now we have the outcomes from that new probability distribution. Let's quit to the main screen and we'll one more time do our, our one variable stats. So you can find that in stat calc, except now my outcomes are in list 4. All right, my probabilities are still the exact same. So it's still list 2. Here we go. So we end up with a new mean and a new standard deviation. So mean of C is $832.50, and standard deviation of C is still 102.80. All right, so it's really important now that we're dealing with multiple random variables and transforming random variables that you're A, naming each individual random variable using a different capital letter, and B, when you're calculating the mean and standard deviation, you're using this subscript notation so that the reader knows what variable you're talking about calculating the mean and standard deviation for. All right, well, notice what happened to our mean from just tuition. It was $732.50. It's now $832.50. Just went up by $100, so our mean just increased by $100. Our standard deviation was 102.80. Continues to be 102.80. So standard deviation did not change at all. Right? So our big takeaway from that is the effect of adding or subtracting a constant to a random variable will add to measures of center and location. So we saw that with the mean, right? It added just the same $100 to the mean. It'll do the same thing to median, quartiles, and percentiles because those are all measures of position. But it does not change measures of spread. It has no effect. And so you can kind of take this back to algebra, like the way transforming a function works, right? If you add a constant to a function, all it does is shift the function. So a distribution is just a function. So if we add to it, all that's going to do is shift the function. And so it is going to move the mean, right? It's going to move the mean by however much you shifted it. But measures of spread are all relative to the positions of the data with respect to each other. So the range isn't going to change. It's still going to be max minus min. It's still going to give you the same thing. And the standard deviation is not going to change either, right? All right, give me your favorite symbol in the numerical keypad when you're done. I like the ampersand. So let's just practice this. In a large introductory statistics class, the distribution of raw scores on a test was approximately normally distributed with a mean of 17.2 and a standard deviation of 3.8. The professor decides to scale the scores by multiplying the raw scores by 4 and adding 10. And so we're going to call y our scaled score. And they want us to find the mean and the standard deviation of y. All right, so first of all, let's define y based on x. So y equals 4 times x plus 10, right? All right, find the mean and standard deviation of y. So here's how we do it, right? Mean of y. Mean is a measure of center. And so we have two transformations happening here. We have a multiplier and we have addition, right? And so remember that multiplication also multiplies measures of center. And addition adds to measures of center. So both are going to impact the mean. So the way I'll compute my new mean is I'll do 4 times my original mean, and I'll also add 10, right? All right, so that's just 4 times my original mean was 17.2, and then I'm going to add 10 to that. All right, let me grab my physical calculator. Hold on. All right, so that's 78.8. So there's our average scaled score. Now, standard deviation of y is a measure of spread. So measures of spread, we do want to multiply by the absolute value of the multiplier. But remember that it does not, addition does not change measures of spread. So we will not add that 10 to our measure of spread. So the way we're going to get our new standard deviation, our scaled standard deviation, is by 4 times our old standard deviation, but we're not going to add the 10. All right, so that's just 4 times 3.8. Which is 15.2. All right, so there's our scaled mean and our scaled standard deviation. Now, what is the probability that a randomly selected student has a scaled test score of at least 90? So the thing we want to take away from this is that they told us the scores are normally distributed, right? And so a transformation will not change the shape of the distribution, meaning it'll still be normally distributed after we've applied these transformations. So we can assume that our scaled score also has a normal distribution with a mean of 78.8 and a standard deviation of 15.2. So I'm just going to sketch that out for myself here. This is my scale scores. My mean is here at 78.8. Got that standard deviation of 15.2. And they said at least 90. So at least 90, let's say 90 is going to be somewhere over here. At least, they mean 90 or greater, right? So we want to know what that area is. All right, if I'm computing a probability, I need to use a probability notation. So I want the probability that y is at least, meaning greater than or equal to 90. All right, and we're just going to use normal CDF in our calculator to do that. So our lower bound will be 90. Our upper bound is technically going to be infinite. Really bad infinite. Let me do it again. There we go. Our mean is 78.8. And I'm going to go down here. Our standard deviation is 15.2. All right. So you can find that in the distribution menu, which is second variables. You want normal CDF. Lower I said 90. Upper is infinity. Mean 78.8. Standard deviation 15.2. Again, if you have the older operating system, this is how your syntax should look. My probability comes out to about 23%, so 0.23. About 23% of the students you'd expect to get an A. Questions on that? This is just a summary of everything we went over. This is symbolic instead of the ones I gave you before were verbal. So this kind of just shows you all in one if you have a linear transformation. So we're transforming x to y. And we're doing that by adding a and multiplying by b. That's called a linear transformation. Then the mean of y will be a plus b times the mean of x. And the standard deviation of y will be the absolute value of b times the standard deviation of x. And that's just because b, it is possible for your multiplier to be negative, but you would always just use the positive version to multiply your standard deviation. All right. Give me a plus symbol in the chat when you're good. All right. So now we're going to talk about combining random variables. So if I have two different random variables, x and y, if t equals x plus y, then I can say that the expected value of t, or the mean of t, is just the sum of the individual means of the random variables. So this is just a formula. Remember, for random variables, that the mean is also sometimes referred to as the expected value. And that'll manifest in like word problems where they say, what do you expect, a randomly selected student's tuition to be? So they're not outright saying calculate the mean of this distribution, but that's what they're asking for if they say, what do you expect a randomly selected value to be? And so you could be combining more than two random variables, and it works the same way. The sum of several random variables is still just, the mean of that would be just the sum of their means. All right, and the only way to determine a probability for any value of t is if we know that x and y are independent. Meaning knowing whether any event in x has occurred tells us nothing about the occurrence of any event in y, and vice versa. So this is a little bit of a technicality, but you have to know that they're independent before you're able to combine random variables. And generally that'll just be stated in the prompt, okay? Or it'll be safe to assume in some way. And I'll show you that in an example. I think we'll be able to get to probably just one more. Yeah, sorry, I don't mean to rush you through that. So you just need to know that they're independent random variables. Don't feel like you need to write everything on this page down. The important thing is to be able to combine random variables, we need to know that they are independent. All right. So here's the thing about combining random variables. To compute the standard deviation, you have to start with the variance. And we haven't talked about variance in a while. We did mention it sort of towards the beginning of the year, but variance is just standard deviation squared. So the way the math works out for combining these random variables is if you know that they're independent and t is x plus y, then the variance of t is equal to the sum of the variance of x and the variance of y. With that in mind, you cannot add standard deviations, meaning sigma t does not equal sigma x plus sigma y. And the reason for that, right, is that sigma t is just the square root of the variance. Yes, that is the case. But that's the square root of the sum of these two variances, which is not equal, this does not equal sigma x plus sigma y, just based on order of operations, right? All right, so last thing, and I already kind of showed you this on this slide, but how do you find the standard deviation of the sum of independent random variables? So once again, sigma t, that's just the square root of the variance, right? Which is the square root of the sum of the variance for x and for y. Okay, and we'll stop there.